Hi everyone, so my name is Akira Sone. I'm currently assistant professor from University of Massachusetts, Boston. First of all, I'd like to thanks for the invitations and organizing of this workshop. So this is the work with Professor Naoki Yamamoto from Keio University Quantum Computing Center in Japan, and his student Akira Tanji, so another Akira. So today I'm going to talk about insights of quantum communication in quantum generative model. So this is more fundamental aspect of the quantum machine learning. So let's talk something very fundamental. So before getting to the topic, so this is my opinion. Actually, this is my opinion. So probably you agree with or you disagree with, but in my opinion, I think right now we're currently living in the age that characterized by two technologies. One is the artificial intelligence, supported by the machine learning algorithm. So, for example, like ChatGPT, the automobile, all of these kind of technologies become matured. And then, however, the machine learning actually are facing to a kind of a problem, like a Moore's law-like trend. That means the curse of the dimensionality is concerning the data set, the size of the data set. So we're expecting that quantum computing might be able to help this problem because of its outstanding and promising capability of the information storage and information processing. So then why don't we combine these two together? So we have a quantum machine learning, and so the people are expecting to use quantum machine learning to solve many problems, such as from the quantum simulations, quantum chemistry, to some new frontiers in quantum metrology, even for some like a machine learning problem. So in my group, actually, so I'm interested about many aspects of quantum machine learning, from the very fundamental things to the practical things. So for example, when I was in the Los Alamos National Laboratory as a postdoc, I was studying the trainability of the variation quantum algorithm. And I was also developing the quantum algorithm, variation quantum algorithms for estimating the quantum Fisher informations for developing a good quantum sensor. So this is the practical side of my work. But I'm also very interested about the most fundamental things about quantum machine learning. So focus one is quantum research theory. So what is a quantum research theory? So when we talk about quantum research, we always mention, for example, the quantum coherence and entanglement. So we use these as a resource to do some task. For example, quantum sensing, quantum computing. So in quantum research theory, we are going to characterize measure the properties of these resources, like coherence or entanglement. So by using it, we expect that from the perspective of quantum research theory, we take the advantage of the tools we developed in the theory, we can analyze or study the physical advantage of quantum machine learning. But on the other side, in the focus 2, I'm interested about open quantum systems and quantum thermodynamics to understand the physical limitations of quantum machine learning. For example, Landauer's principle. So basically, Landauer's principle says, basically gives you the minimum minimum heat for erasing one bit of information. And this is characterized by the second law of thermodynamics, right? So the question is, okay, then we extend it into the quantum version of the quantum Landauer's principle, for example, and how can we address the physical limitations of the quantum machine learning? So basically, I'm trying to ask about like the bright side of the quantum machine learning and the dark side of the quantum machine learning, okay? So, and today's talk mainly focuses on the generative model. So let's think about a simple classification problem. So you have a hidden distribution of the data, let's say xi, and then you, through the generator, you have the new sample of the data, and you put it into, let's say you can get the probability distribution px. And then you send it to the neural network, which can be characterized by the conditional distribution, and then you do the classification, basically labeling the data. And this is characterized by the marginal distribution. So, and then the question is, how can we measure the quality of the generative model? A very old measure, this is a very old measure, right? It's a very old measure of the quality of the generative model is called the inception score. I know for some people, for the people from machine learning community, people say, oh, we don't use it anymore. But actually, this measure actually can give us a very deep physical insights. Okay, that's why I'd like to focus on this. So what is the quality of the generative model? The quality measure actually this guy will actually measure two things. So one is the accuracy of the image. So we hope that the generated image is close to the real image. So if there is a cat, so you want the condition distribution to be sharp. So in other words, you want to have the smaller entropy regarding to the accuracy of the image. But also we hope that we can generate various images. And this is characterized by the margin distribution, and you hope the margin distribution is kind of like flat. So this can be characterized by the larger entropy. So you want to have both of them. So this is what you want. The good generative model looks like this. And then what you want to do is we want the distinguishability between the condition distribution and the margin distribution to be larger. This is what we want. So a good measure in the classical information theory is this relative entropy, KL divergence, which is basically the relative entropy of your yes?
I'm sorry, why do you want the generated image distribution to be uniform?
Because you want to have the various. If you want to achieve the more diverse images, you want the distribution to be flatter, like that, so that you can, classify into the various.
In an application scenario, I would just give it a prompt and hope it'll generate the image, not some, random uniform distribution of all kinds of images.
Well, for that one, this is the accuracy of the images related to the conditional. But still, you want your generator to generate the more diverse things, so it's a flatter one. Right. So this relative entropy of your condition distribution with respect to your margin distribution can become a good metric. So the inception score in the classical machine learning is defined by this exponential of the averaged relative entropy. So the larger inception score is, the better the quality. So this is the definition of it. So then we have this classical generative model, and we have this classical inception score. But the question is, when we extend it to the quantum generative model, can we have the quantum analogy of the classical inception score? So we call this is the quantum inception score. So suppose that if we can have this quantum inception score, the question is, can this quantum inception score be larger than the classical inception score? Yes, please. Yeah.
In the classical case, what's the maximum score one can pass?
Excuse me?
Maximum possible score.
What's the maximum possible score? Yeah, so you will see that later. This is called accessible inception score. You will see. Well, actually, the maximum is infinity because relative entropy can be infinity. It's super large.
So does that mean like you can accurately generate image of a cat and all kinds of animals, something like that?
Yeah, yeah.
Finance are perfect.
So the question is, does this quantum generative model can outperform the classical generative model in terms of the quality? And second question is, if yes, then what are the resources for this advantage? And intuitive answer is entanglement and coherence. But we need to prove this mathematically. And the third one is, what causes quality degradation of the quantum generative model? And intuitive answer is quantum decoherence. But the question is, how can we quantify it? So this is the third question. So now let's think about the following model. So first we have a quantum generator, and then we encode each data into a quantum state. Let's say rho in xi. Okay. And then the quantum generator produces rho in xi with the probability x, pxi. And you can get the quantum, through the quantum classifier, you get rho out I. And this rho out I is dependent on the quantum data. Okay? And then let's define this E as the output ensemble in this form. And then we just have to change the classical relative entropy into quantum relative entropy. So, and we define the quantum inception score like this way. But this is actually very inspiring. Why? Because this part is actually horrible information. So then the physical picture becomes super, super clear. Why? Because the horrible information is related to so-called classical capacity, that is the maximum amount of the classical information transmittable through the quantum channel phi. So now we connected the quality of the quantum generative model with the concept of the quantum communication, how much information we can transmit through the quantum channel. So the more information you can transmit, the better your quality is. And actually, this is very much aligned with our intuition, physical intuition. So let's see how it works. So now you have a quantum inception score. And then so this is the so this part right here is the horrible information. And then we can actually, how can we relate it to this? Relate this to the classical capacity is the following. So we have the so-called whole-level, sorry, I don't know how to pronounce this very well. So HSW capacity, which is the maximization of your whole-level information over your ensembles. And then we prepare many copies of the quantum channel phi in asymptotic limit. And then we can define so-called regularized classical capacity. And this one actually corresponds to the maximal transmittable amount of the classical information through the quantum channel phi. If we have the entanglement input, so we have many copies of the quantum channel, if your input are all entangled with each other, then with some phi, we can achieve this C phi, this regularized capacity, is larger than the HSW capacity, which is larger than the whatever information, which is larger than the whatever information. So we have the entanglement enhanced quantum inception score. All right. So that means quantum entanglement could enhance the quality of the quantum generative model by defining the quantum inception score. We can also recover the classical inception score from the quantum inception score through the projection measurement. So this is the quantum inception score. And if you have a projection measurement, you can actually recover the classical one. Okay? And so now this is a projection measurement, but you can also generalize it into the POVA measurement. And The maximization of the Hollywood information over all the pure VMs is corresponding to the so-called accessible information. So here you can get the accessible exception score. And this is the largest, the largest classical exception score you can achieve. And then Holevo, in 1937, derived a very important formula, a theorem. He said, if the Holevo information is larger than or equal to the accessible information, the Holevo information is larger than or equal to the accessible information, but with equality if and only if this row out n and this row out m, basically the component states, are commute with each other for all n and m. So then we actually derived one theorem, and this theorem basically states that the quantum generative model have a better quality than the classical generative model. But then the question is, what is the resources here? And that's actually coherence. But then how can we quantitatively see the coherence actually contributes to quality, contributes to the advantage of the quantum generative model? So we have to use a measure of the quantum coherence, which is called asymmetry. So now let's think about the time translations. When we say, and given the quantum state rho, when this rho is commuting with h, we call this symmetric, because the rho is diagonal in h eigenbasis. But when rho is not commuting with h, this is asymmetric. And so what happened is there exists a non-zero of diagonal elements in h eigenbasis. Rho has a non-zero of diagonal elements in h eigenbasis. And this non-zero of diagonal elements actually characterize the quantum coherence. So we define a symmetric ensemble like this, where that means the component states are all commute with each other, and a symmetric ensemble means that there exists a pair of component states that do not commute with each other. Then we prove that when the quantum exception score is larger than the accessible exception score, if and only if the ensembles of your output states is a symmetric ensemble. So from this theorem, we can quantitatively say, yes, coherence actually play important roles in the advantage of the quantum generative model. So this is the idea. So the third question is the quality degradation due to the decoherence. We know the decoherence should be the major cause of the quality degradation. But the question is, how can we quantify it? So we have proved that the theorem 3, so the quality degradation of the quantum generative model is quantified by the so-called quantum efficacy. So what is that? This gamma right here is coming from so-called quantum fluctuation theorem. And the quantum fluctuation theorem is a generalization of the quantum second law of thermodynamics, which is mainly discussed in the quantum thermodynamics. So this makes a lot of sense, because second law of thermodynamics is a Lambda's principle. A Lambda principle basically is about physical limitations of the machine. So of course, quantum fluctuation theorem should kick in characterizing the quality degradation of the quantum generative model, because this is about the physical limitations of the quantum generative model machine. Right? So we have obtained this formula. And actually when gamma equals to 1, we have figured out the all constituent states, component states have the same eigenbasis. So they're all have the same diagonal eigenbasis. So roll out becomes incoherent state. So from this analysis we characterize, so basically when gamma is getting closer to 1 is more classical, when gamma is getting to 0 is more quantum. So negative gamma accounts for the information contents contained by the quantum coherence. All right, so this is the, so now let me summarize the results. So this has been published in the Physical Research. So in this work, we proposed the quantum inception score. And this quantity actually help us to connect the idea of quantum communications to the quality of the quantum generative model. And we have verified that the asymmetry is the resource. Asymmetry means the quantum coherence is the resource for the better quality in the quantum generative model. And entanglement could enhance the quality further. And yes, the quantum decoherence is the main reason for the quality degradation. But this can be quantified by the so-called quantum efficacy that is developed in the concept of the quantum fluctuation theorem. So from this, we can see that the quantum foundations approach to quantum machine learning is very, very important for us to really understand how the quantum machine learning works. So further, we can think about how to use, for example, this quantum inception score to do some applications. For example, the characterization or the classification of the quantum phase in the many-body systems, et cetera, et cetera. So this is like our next step to explore. All right, so this is the end of my presentation, and thank you very much for attention.
Thank you for the nice talk. So one can view the success of generative models as in part stemming from the fact that the space of natural images as a whole is much smaller than the space of all possible images. And then you also have the additional requirement that you want maximum distinguishability between the marginalized distribution and the probability over natural images, which I emphasize is much smaller. What would the analog of that be in the quantum generative model case? Or is there any statement you can make about the implications on the difficulty of making a quantum generative model?
Wow, that's a very good question. To be honest, I haven't thought about it yet. So yes, I need to think about it. I'm sorry, I cannot give you the clear answer right now. I'm sorry. Yeah, but I think that's a very important question to ask. Yes.
Other questions? Do you have any kind of model system where you can kind of quantify the advantages that you get from the quantum machine learning? I mean, you gave us formulas, but I don't have a sense of quantitatively how.
Okay, so this is the applications actually. So I think one question is, okay, what's the advantage of using quantum inception score in a practical meaning, right? So then actually many people ask me about the questions of scaling, but I don't have a really good answer about that right now. But I can give you some like examples of application. So we actually use the quantum inception score as a cost function to do the quantum phase classification. This is actually, we adopted the same model that the Sone adopted in his QCNN paper. But Sone is going to talk about this next Friday. So what we did was like we are considering this a 1D spin chain problem, and then we use the so-called quantum convolutional neural network QCNN to classify the the quantum phase, three phases, SPT, and then paramagnetic, and then antiparamagnetic. And so we assume that the quantum generator has a perfect performance. We assume. But actually, we want to also optimize it, okay, in the futures. But let's assume it has a perfect performance, and then we just want to classify it. And then, so we did this. The QIS actually is 1.123. And then we optimize the measurement, and then we achieve actually when we have the accuracy of 0.98, classical exception score is 1.022. So as you can see, the QIS and the classical exception score is very close to each other. But this is because we use the qubits, the number of the qubits is very small. So, but in order to see the advantages, I would say definitely you have to increase the number of the qubits, but now this is very hard to simulate because we use classical computers to simulate this. So hopefully, but in the futures, we can see these differences to see the questions of how quantum essential score can scale, in terms of the number of the qubits. So this is kind of the future questions, but now I can just only show you this specific examples.
Okay,
That's it.
Any other questions for Akira? If not, let's thank him once more.
Yes, thank you very much. Thank you very much.